Hey, what's up coders, I'm Coderious and today we will upgrade our A-star pathfinding algorithm to a multi-threaded version. In RTS game we usually control not only one but several units and need to calculate several paths. We could calculate them one by one, but as the function is exactly the same for each unit, we can take advantage of parallel computing offered by modern multi-core CPUs. In Unity we can also use the burst compiler to speed up the operation even more. The starting point of the video is the code I've explained in the previous video. We will make adjustments to upgrade the single-threaded version of the program to a multi-threaded version. You're welcome to follow along or look at the code available on GitHub. Before we start, take a moment to like and subscribe, and I'll see you in Unity. The first thing I wanted to change is to use floats instead of integers. At the beginning I wanted to speed up the process by not using floats and square roots. In theory it's fine, but the problem is that diagonal moves have the same cost as making two straight moves, a cost of 2. The idea is not completely useless and I think it would work for games where we only move in the 4 directions, up, down, left and right, but not in diagonals. Alright, we start with the same packages and change our G-score and H-score to floats. We also add the F-score value in the node. That way we calculate it only once. We use several starting points and save them in a hash table, as we did for obstacles. It means that in the start function we don't initialize our start node but our start hash table. There is nothing to change in the update loop. With this new hash table we can update the clearTile function and reset the starting points the same way we reset our obstacles. Same for the place start, we can duplicate the code we have in place obstacle and change the reference to the start hash table. Another small difference is that we add a new node as value in a hash table instead of a boolean. So we create a new node with the coordinates we just calculated, int.0 for the parent, 0 for the G-score and float max value for the H-score. Okay, I tried few things before ending up with the solution presented in this video. First I tried to create native arrays of native hash maps, but it's not authorized by the compiler. I also tried the version with array and indices of the nodes in the array, but the code did not look really nice and the performance was not where I wanted it to be. So the solution I retained for the video is one where we keep only the obstacles, the offsets as well as a native container for starting points. Next, the results of the pathfinding algorithm for each starting point will be stored in a NativeMultiHashMap. The NativeMultiHashMap is like a standard native hash map, but for which keys can be linked to multiple values. This is perfect in our case as for each start we want to keep a list of nodes heading to the destination. The global list of nodes visited by the algorithm and the open set will be created at runtime in the job. We will get to that in a moment. Alright, to prepare the job we can copy all the starting points from the hash table to the native array. The offset array will also be initialized here to avoid having to initialize the array in each job separately. Then we create the job with the updated parameters and schedule the job. The parameters are slightly different as it is a multi-threaded job. The first parameter is the number of jobs to be executed, which is in our case the number of starting points. The second parameter is the batch count. Unity documentation recommends to start with 1 and increase until the performance gain is no longer material. I'll use a value of 16. As for displaying the result, we will do something a bit different this time. We'll get to that shortly. Finally, we dispose of the native containers used in the function. Great, in the job we no longer implement iJob but iJob parallel for multi-threaded jobs. First we reference our native containers. The obstacles, starting points and offsets array are read-only. The NativeMultiHashMap requires the keyword native disable parallel for restriction. It sounds complicated, but the container is shared and various threads will have access to it. In our case it is in a controlled environment so we can get rid of the restriction. In the execute function we need an integer. I use the letter R but you can use any letter or variable name. This is a reference to the job number being executed, and in our case it defines which starting point we are working on. I explained the job system and multithreading in more details in my other video, have a look in case you are not familiar with the concept. As mentioned earlier, we create our global node list and the open set in the job. In this case, the allocator can be changed to temp instead of temp job. The memory allocation is faster that way. The first current node is extracted from the starting point array at the position R. Another change, as the native hash map is now created in the job, is that I move the closest node function inside the code. In addition, the f-score is now a variable, so we can just compare the variable instead of doing the calculation. The rest of the function is pretty much the same, we just need to calculate the f-score and add it to the node values. While we are here, we can also update our square distance function and rename it distance. It will return a float. We also change the type of a and b to float and return the square root of the previous value. Okay, the last thing we want to do is to copy the solution in case there is one. We do that outside of the do while loop. So in case the node list contains the end coordinates, it means we found a way. In that case, we loop back from the end node to the start node and add each node to the multi-hash map. And at the end, we can dispose of the hash map created in the job. Alright, the process of retrieving the values after the job is a bit different, as this time we have a native multi-hash map with the results. What we can do is extract the key value array from the list. It's not so easy to navigate a key value array, so let's quickly transfer this to another data structure. I thought about a dictionary where the key is the start node coordinates and the value is a queue with the waypoints along the way from A to B. So we loop through our key value array, and if there is no record for the current starting point, we add it to the dictionary and create a new queue, to which we enqueue the first waypoint. If there is already a record, we enqueue the next waypoint. Easy. Great, now let's move the units around instead of just coloring cells. That should be a bit closer to the game mechanics of a 2D game. We loop through the keys of our dictionary and call a coroutine for each of them with the start coordinates and the respective queue of waypoints as parameters. Okay, in 2D games, characters are most of the time represented by a sprite. We can create a simple prefab with the PNG we used for the tile, or any sprite. Drag and drop the PNG file in the hierarchy and drag and drop it back to the project folder. Then delete it from the hierarchy. In the code, we need a reference to that prefab, so we create a new public game object, call it tile prefab, and save the project. Alright, then we create our function to move the units. The function will be executed as a coroutine. Coroutines are executed asynchronously. It means that they run in the background without stopping the rest of the program during their execution. It's clear that when we send a unit from point A to point B, we want to be able to do other stuff in the meantime, like building a base or controlling other units. That's what coroutines are for. Coroutines start with the keyword IEnumerator. Make sure it is IEnumerator and not IEnumerable. It happened to me once and it took me an hour to figure out what the problem was. First, we need to spawn our unit, which translates the coordinates of the starting point into world point with the function getCellCenterWorld and instantiate the prefab at this position. Then we can start providing the waypoints to our units. We get the first waypoint with the function dq. Then we loop through our list of waypoints until there is no waypoint left. We get the coordinate of the next waypoint the same way we did for the starting point, with getCellCenterWorld. If you use cell gaps like me, we must deduce half of the cell gap value to the x and y positions. Then we move our unit in the direction of the next waypoint until it is close enough. When the destination is reached, we get the next waypoint in the queue. We can destroy the unit at the end of the function, but that's totally optional. And that's it, we have upgraded our code to a multi-threaded version. Let's give it a try. We can place multiple starting points and a goal, and voila! The performance is quite good. With the burst compiler activated and few starting points, we are still below 1 millisecond. The first execution is always a bit slower due to how the burst compiler works, but still the performance is acceptable. We can also control the movement speed with a variable. At the beginning of the script, let's add a new float variable and call it unit speed, with a value of 5. In our coroutine, we then multiply time.delta time by the unit speed. If you try again, that's much more satisfying. Alright, it's already the end of the video, I hope you liked it. If that's the case, take a moment to like and subscribe. As always, the project is available on GitHub, and if you check, you will see that there is another implementation of the A* algorithm next to the version presented in these videos. This one replicates the pseudocode version from Wikipedia. For some reason, my version runs almost twice faster, depending on the case. It would probably require a thorough analysis to tell if my implementation has flaws. Let me know what you think in the comment section and how you have implemented A* on your side. You can also join me on Discord, where we'll be posting some news about the channel and my projects. And we have reached 100 subs! Thank you guys for following me, thank you for watching, keep coding, and see you next time.